One way we can use this idea of heat transfer between two objects is through this process called calorimetry. So, under perfect conditions, if you take two objects that are at different temperatures and you mix them together or put them in contact, the energy that's lost by the higher temperature object is exactly gained by the lower temperature object. So in other words, the heat is transferred from the higher temperature object to the lower temperature object without loss to the environment. So this is kind of like conservation of energy, right? So you have each object has a certain amount of thermal energy associated with it, and so one object is losing thermal energy and the other object is gaining exactly that thermal energy that was transferred. So some examples would be when you take cool milk and you add it to coffee. It cools the coffee and warms the milk. A hot metal forge is submerged in water, so hot metal that's in a forge is submerged in water, so this is probably something you might see in movies where you take, that hot metal, they're trying to make a sword or something like that, right? Have it in the heat, and then they stick it in the water, it cools the metal and it warms the water. And of course, ice cubes added to tea cools the tea, warms the ice, and so on. So all of these processes are important in the sense that we assume that energy is conserved and none of it leaks out to the environment. Now, in all of these examples, there is some loss to the environment, but if we had a closed container that we could keep that energy transferred just between the substances, then we would have this special case of a calorimeter that we could use to look at that transfer of energy. So let's look at an example where we have a 75-gram piece of some unknown material and it's heated to some initial temperature of 65 degrees. The material is then placed in 150 grams of water that was initially at 15 degrees. When the system reaches equilibrium, the temperature of the mixture is 20 degrees Celsius. So they've reached thermal equilibrium. The energy transfer has stopped happening. We want to know what is the heat gained by the water, what must be the heat lost by the unknown substance, and then can we use that information to figure out the specific heat of the unknown. So in this particular case, it's a good idea to create a table, and we can look at which object loses energy, the one that's at the higher temperature, and which object gains energy. And we can go through and let's read the question again, and then we're going to fill in information in the table. So I have a 75-gram piece of an unknown material that's heated to an initial temperature of 65 degrees. So I know that my metal is at the higher temperature. So it's going to be the object that loses energy because it starts off at a higher temperature. It has a mass of 75 grams and an initial temperature of 65 degrees. It says the material is placed in 150 grams of water that was initially at 15 degrees Celsius. So I have the object that's going to gain the energy when they come in contact is the water, which is initially cooler, and I know its mass, and I know its initial temperature is 15 degrees Celsius. The two are mixed together and eventually they reach an equilibrium temperature so that both of them have a final temperature of 20 degrees Celsius. We want to determine what is the heat that's gained by the water, the heat that's lost by the unknown, and so on. The other thing that we don't know at this point is what the specific heat of the metal is, right? So what is the specific heat of the unknown metal? We want to find that. But we do know the specific heat of water in units of calories, gram, degrees Celsius is 1. It's not stated in the problem, but we've done enough with water that we would have to remember that, that's something that's pretty standard and we could look that up. All right, so before we go on and we actually answer these questions, we are going to be interested in how the temperature of these two substances change. So I can look at how does the unknown piece of material change temperature, and it changes from 65 to 20. I don't care at this point about which is at the higher temperature. This is actually just the amount that the temperature changed. So obviously the final is smaller than the initial, so the delta T, final minus initial, would be negative 45, but I just care about the number, like how much did the temperature change. The metal changed by 45 degrees Celsius versus the water, on the other hand, which started at 15 and ended at 20, changed temperature by only 5 degrees Celsius. So let's think about this for a minute. Why does the water not change temperature by the same amount? Well, there's two reasons. There's more water, right? There's twice as much water as the metal, so I would expect that the water's not going to change temperature as much, but it's still not like close, right? This is 45 and this is 5. The other reason is because water has a high specific heat capacity, so this number here is going to be a pretty big number compared to our answer that we get over here. All right, so we'll keep all that information there and we'll answer each of these questions individually. So what is the heat that's gained by the water? So I can pretty much ignore the substance here and I'm going to focus on what's going on with the water. And I want to know what is the heat, the Q value, that was gained by the water when it changed temperature by 5 degrees and it had a mass of 150, and I know its specific heat capacity. So the heat that was gained by the water would be 150 grams times 1 calorie per gram degree Celsius times 5 degrees Celsius, which is 750 calories. So when these two are mixed together, the water gains 750 calories of energy. That heat is transferred 750 calories. What must be the heat lost by the unknown substance? So the water gained energy, and in the process, the unknown material lost energy. So in calorimetry, no energy is lost to the environment, so the energy, the heat gained by the lower temperature object is exactly equal to the heat that's lost by the higher temperature object. So that means that the heat that was gained by the water, 750 calories, is equal to the heat that was lost by the metal, so 750. We now want to know what is the specific heat capacity of the unknown substance. So we want to figure out what is this value for this metal here. We know the specific, we know the heat that was lost by the metal is 750 calories. We know its mass, we know its change in temperature, so we can determine the specific heat capacity of the metal by taking the energy that was lost, transferred, divide by the mass and the change in temperature. For the unknown substance, we know that it was 750 calories that was lost. The mass of the metal is 75 grams, and the change in temperature over here was 45 degrees Celsius. So I end up getting that the specific heat capacity of this metal was 0.22 calories gram degree Celsius over here. And if I compare these, this specific heat capacity of the metal is much smaller than the specific heat capacity of water, which means that it's going to change temperature by a greater amount compared to the water. It also has a smaller mass, but regardless, even if they had identical masses, this change in temperature would still be greater. So I wanted to consider a couple of different conceptual questions. So let's consider adding the same amount of energy to two different amounts of a substance. So suppose that we add a certain amount of energy to a given amount of a substance, and the substance changes temperature by 20 degrees Celsius. How much will a second substance made of the same material change temperature if we double the amount of heat that's added? So basically, it's like I have water, right? And I have a certain amount of water, and I add energy to it, and it changes temperature by 10 degrees Celsius. And now I want to know how much will a second substance made of the same material change temperature, same amount of the substance, right? But I double the amount of energy that's put in. So how will it change temperature? So I know that for the first case, I have a certain amount of energy added, I have a certain amount of mass, and I have the specific heat of the substance, and I get a change in temperature of 20 degrees Celsius. In the second case, I am doubling the amount of energy I put in, So my Q value is twice as big, my mass stays the same, and my specific heat of my substance stays the same. So if I go back and I look at how the temperature change is affected for my substance for the first case, the change in temperature depends on how much energy is added, the mass, the specific heat of the substance, and now in the second case, I'm adding a different amount of heat, same amount of the substance, same specific heat capacity. So I can plug in the fact that the energy added is twice as much, the mass stayed the same, and I have the same specific heat. I can factor out the 2, and I realize that what's left over here is just exactly what I had over here, right? So the heat that was added in the first case, so there's twice that amount of heat, the mass stayed the same, specific heat, and so the temperature change for the second case will be twice what it was in the first case, so it should be 40 degrees Celsius. So if I add twice as much energy, the change in temperature is directly proportional to the energy added. So if I double the energy right here, right, I've doubled this quantity, I'm going to double the change in temperature. Suppose we add a certain amount of energy to a given amount of the substance, so this is the same thing as before. How much will a second substance made of the same material change temperature if we add the same amount of energy to twice as much of the substance? So now I am going to have the same starting point that I had before. I have a certain amount of energy, mass, specific heat, and the temperature changes. I'm adding the same amount of energy, so that's going to stay the same to my second substance, but my mass is now twice as big, and I have the same substance. So I know the change in temperature for the first case is the heat added over the mass specific heat. And now I want to know, how does the temperature change under the second circumstance where I add heat to mass specific heat? I know that the heat added, the Q in the second case, is the same as the first, but my mass is now twice as big, right? So it was M1, now it's twice as big. I look at these terms here and I realize that this is exactly the same as what I had before, right? The heat, mass, specific heat. So, and the 2 is on the bottom, so my change in temperature is going to be half of what it was before. It was 20, so it's going to be 10 degrees Celsius. So what is this saying? This is saying that the change in temperature is inversely proportional to the mass. So if I double the amount of mass of my substance, the change in temperature is going to be half as much, right? I have more of the substance and I'm adding the same amount of energy, so it's not going to change temperature as much, but they're inversely proportional. Doubling the mass means the temperature decreases by a half. So those were specific examples of just adding energy. Now let's think about mixing substances together. Suppose we mix 1 liter of water at 20 degrees Celsius with a second 1 liter of water at 20 degrees Celsius. What will the final equilibrium temperature of the mixture be? Oops, I went ahead there. Since both containers of water are already at the same temperature, they're not going to exchange any energy. So the final temperature is just going to be 20. In order to mix two substances together and see any effect, they have to be at different temperatures, right? So you have to have them be at some slightly different temperature to see some temperature difference. So now it's just going to be at 20. Suppose now we mixed 1 liter of water that's at 20 degrees Celsius with a second 1 liter of water at 30 degrees Celsius. What will the final equilibrium temperature of the mixture be? So I have the same amount of water. I have one container of water that's at 20 degrees Celsius and one container of water that's at 30. And I mix them together, and it's equal amounts of water. Since both of the containers of water have the same amount of liquid, but are at different temperatures, the container at a higher temperature has to lose energy, and the container of at the lower temperature will gain energy. the energy that's lost has to equal the energy that's gained, right? So higher temperature has to equal lower temperature, or let me say that again. So the lower temperature object is going to gain energy, the higher temperature object is going to lose energy, and the energy that's lost has to equal the energy that's gained. So we know mass specific heat change in temperature for the water that gained energy has to equal the mass specific heat change in temperature that was lost. So in this example, I have 1 liter of water and 1 liter of water. So both of these masses are the same, right, for both of these liquids. They're also both made of water, so their specific heats are also the same. So what that means is that the change in temperature of the mixtures has to be exactly the same, right? Because it's the same amount of the substance, the same specific heat. And in order for the both containers to change temperature by the same amount, the final temperature of the mixture has to be halfway between them, 25 degrees Celsius. So that should make sense, right? So I have equal amounts of water. I mix them together. And so when I mix them together, the temperature is going to be halfway between what the two different substances were, right? So at 25 degrees Celsius, the 20 degrees Celsius water will increase by 5 degrees Celsius, and the 30 degrees Celsius will decrease by 5. Suppose we mix 1 liter of 30 degrees Celsius water, 1 liter of 20 degrees Celsius water with a second 2 liters of water at 30 degrees Celsius. What will the final equilibrium temperature be? So now I have more warm water than I have cold water. It's not going to be halfway between anymore. The second container of water has twice as much liquid in it. So the container at the higher temperature will lose energy, and the container at the lower temperature will gain energy. We still have the fact that the energy lost has to equal the energy gained, right? So mass times specific heat times change in temperature of the lower temperature object that's going to gain energy has to equal the mass specific heat change in temperature of that's lost. So this one is a little harder to explain, but we have to think a little bit about what's going on. So if I put in my values here, the specific heat is the same for both of these, right? Because it's water, so that cancels out. But what's happening is that the substance that was at 30 degrees Celsius had 2 liters of water, it had twice as much mass. So on the lost side, the mass here is 2 times as big as this one, which means that the change in temperature of the substance that was at a lower temperature that gained energy has to be twice as much as the change in temperature of the lost object. All right, so let me say this in words and then I can read this over here. So basically, you've got a lot of warm water at 30 degrees Celsius, you've got less water at 20 degrees Celsius. When you mix them together, because you have a lot more of the 30 degrees Celsius water, it's not going to change temperature as much. Versus the 20 degrees Celsius water, you have less of it, so when you mix them together, its temperature is going to rise more. So the change in temperature of the cooler water, the one that gains energy, is larger than the change in temperature of the warmer water because there's less of it. The cool water has less mass, so it will change temperature by a greater amount. Since 25 degrees is the temperature at which both substances change temperature by the same amount, the final equilibrium temperature would have to be greater than 25. So if it's greater than 25, it causes the lower temperature object to change temperature by a greater amount and the warmer object to change temperature by a smaller amount. So the final equilibrium temperature here is going to be greater than the halfway point because the warmer water holds its energy more, right? So it's not going to change as drastically as the 20 degrees Celsius water because there's less of it. So it would be greater than halfway point because there's more of that 30 degrees Celsius water.